go. Okay, welcome back. So one thing of logistics. Oh, it would help to turn on the screen, huh? So that everyone can see what I see. It wouldn't hurt. All right, it's coming. But I enabled discussion so you can add discussion posts in Husky CT. Week or two, like when we first started, I offered a few different options. It seemed like the goal was reduce the number of times you have to log into different softwares. I'm down with that. It sounds good. So this is a place, let's see. I didn't delete that. Oh, maybe anyway, but you can add a discussion post. I'll keep an eye on it. I'll have TAs also keep an eye, but also take a look at it because it'll help. Like if you read questions or you post questions, like the way you create questions and think about them, sometimes that leads to good answers anyway. So I wanted to have some kind of asynchronous Q&A, like questions and answers here. Yeah, so that's main logistics. Then let's check on where we're supposed to be. Goal is that tomorrow we submit homework 1. How is it coming along so far? No issues. Seems like we're going pretty well. At least from the things that I've seen, it seems like people are having the right amount of trouble with it. Like it's not going to be easy. Like you're trying to learn something new, you're trying to remember things from before and apply them to new places, but it seems like we're on the right track. And then once we turn that in tomorrow, on Friday we can start taking a look at project 1. That'll be our first little more open-ended kind of work. Where are we starting today? Questions, are there conceptual questions, hands-on like Python questions, existential questions? Where are you at today? Is my computer really thinking when I tell it to do this work for me? Are these zeros and ones actually consciousness and it's deliberately angry with me? That's why I get so many error messages. All right, let me check in, see where we're at, and then we can do either demos or answer questions that way. What is the question 42 is the answer for? 2 times 21. That's the meaning of life. It's 2 times 21. I feel like you can run this in Python. Let's double check. Yeah, it does work. You can install pip install answer to life. But I'll have to restart the kernel. Sometimes, because we're using like a server that's kind of managing things for us, pip install, I've had trouble getting things to be like persistent. but this is between pip install and conda install, and then like import functions. That's why Python is so popular, because it's so easy to kind of like make a quick tool that does something that you need done, install it, run it, done. Like, so it's great to know. Like, we're diving into like some of the computational work of like numerical methods and scientific computing, but Python's really powerful because you can, like when I was a grad student, there was a whole software toolkit for Abacus, for finite element software. So I could run Abacus through Python, like tell my finite element to change things, run it again, pipe out, like post-process the output, check the result, and then run another finite element. So over the weekend, I ran 10,000 finite element simulations, and then when I got back on Monday, I had like the optimal solution, which is pretty amazing. Like, to do that by hand would take you months to like go through all of those, and maybe you would do it in more of a smart way than just like a brute force, keep running and looking for optimal. But it is pretty amazing that you can do all of that. So it's a great like glue language. As numerical method, like the stuff that we're working on, it works great. It's a good way to get things done, but it's even more powerful as a glue to kind of stitch together all of your work. Anyway, so that's 42. I know we were working on getting things fixed. Like, more questions? You just didn't want to share them? Yeah.
It's hard to share what the users. I was wondering if they're supposed to be important users. What seems like they're supposed to be important.
Oh, it's supposed to just go ABC.
Is this what the is supposed to be?
Oh, from the reading, there's acceleration by taking the derivative twice. So it's two different ways. Like, one is if you know position as a function of time, you can derive it twice. Other option is I know what position should be, like I know what function it should be, so I'll do a fit and then take a derivative of my fit rather than my actual numbers that I calculated. You're working way ahead, trying to like get it all done before Halloween. Done with the class. Nice. Yeah. Any group work on anything?
No, I think I have.
Okay.
I just wanted to see them like watching them.
Okay.
Yeah.
Okay.
No question. No immediate questions.
Okay. Just kind of like checking on things.
Yeah.
Yeah. I guess the only question. Oh, to submit it? Yeah. You can put like on the file button in the top left and make it print screen. Yeah, and then make it print. Yeah. That was the only question. I know. And like ideally I would just take the notebooks, but you can't do anything in CCT. I don't like right away. Yeah, any questions? No. Okay. Okay. Which parts were you?
Well, I was sick a few days.
Yeah. Okay. All right, so this question came up a couple of times, and it comes up pretty often. It's like, how do I actually submit this work? The Jupyter notebooks don't show up in Husky CT, so we have to do like PDFs for everything. And the quickest way that I found is create a print preview, and the print preview is like a static web page of all of your work, and then print that to PDF or save as a PDF. And that works really well. So when I make that print preview, it kind of comes up, it shows me all of my work. And like it looks good to me, so I can say Control P or Apple P if you're on Mac. And then for me, I would say like save as PDF, or sometimes there's an option to like print to PDF. Yeah, exactly. So like hashtags, those are great when you're actually looking at line by line, what did I do here? And it's really helpful to go back. What did I do? The help file is really good when you start looking at lots of versions. Like we were just talking about importing. Let me take this thing that I built in Compact, import it into this code that we do for e-transfer. Yeah. Then you ask for help and it just says like, no gotcha. So instead we give it like a comment. Yeah, a little bit down to so we time it. Don't want to time everything. So right now, it's kind of like this. It's importing something. It is doing this, doing that, doing all this. It's pretty tight. It's figuring out how long it's going to take for everything. So for this, what you want me to do two separate well, like mean standard deviation, you're going to do that on both problem one and problem two. Right. So that one, we don't really care how long it takes. It should be the same amount of time. The difference that we're looking for is if we use 4 to 6, not 5 and a half. Is there a difference? There should be. It should be a lot faster setting versus really the only there's also we're trying to do everything in one cell, one block. There is import yeah, it's always the first line. It's going to time everything in the cell. So you don't want to import stuff. Yeah. Like you don't want to print anything. You don't want to import anything. So this feels good. Yeah, yeah, exactly. Like, this is because now you know that in order to do these two loops and store results, it takes 60 cycles. Like actual computation. So for it's just choosing well, the main thing is like you can change it, right? Does it work? Right. So if you're like icon developer, you break these like test you're looking at this and run an example. Right. It's supposed to interpolate and so that will be the next thing to do to show that you see it themselves. This one. Yeah. So just an example of that. Okay. No one else asks about it, but usually there's questions about this. When you run, there is no error. I think it's kind of like a step process. You have to figure out how to make an error and how to fix the error. Okay, so I wanted to bring this up because we were talking about it in the back of like, what do we do? We're told that there's an error, but if I run this code, I don't get an error, right? Like if I grab that function, put it in a cell, run it, there's no error. Why is that? Why is it not? Because I'm telling you that there's something wrong with it, but I'm not actually seeing anything wrong. Yeah.
Same thing to actually run the call the function and see that there's an error.
Yeah, and this is Python specific. Like some languages will check, like C++ will go through your functions and check to make sure that they work. Like they have some kind of test case, so if you make a function that's not going to work, it won't actually compile. But Python, if you make a function full of errors, until you run that function, you'll never know that there's an error. So this is kind of like a two-part, 2, 3, I don't know. There's levels. It's an onion of Python onion problem. You gotta peel back the layers of problems. So the first step is like, all right, I need to actually try to run this and see what the error is. And I think like a lot of people kind of saw what the problem was to begin with, fixed it, and said, hey, I fixed it. But well, let's go through and pretend like we didn't know. Now I can start kind of tracing back what was the cause of this error. So at the bottom, I always read from bottom to top because the bottom line is always the most informative. Like there's an index error, index was out of range. And then I move my way back up to the top. Like, all right, well, where did that happen? It happened here when I tried to calculate slope, and that happened inside this function. So now I can go back up to this function and say, all right, well, what's wrong with this slope line? Like when I calculated slope, somehow my indexing was out of range. And here, because we're Python, it's base 0. So the second value in that P2 and P1 is actually 1, and the first one is 0. So I can change those indices. So I can change this to a 1, change that to a 1, 0, and 0. But I'm still getting an error. What the? So getting the same error is good as long as it's moving locations. That means you fixed one problem, right? Like, that's progress. Errors are totally fine. You should be getting errors if you're doing something interesting. If you never get errors when you're coding, then that means like, I don't know, everything's like in a cookbook, like it's already made for you, and you're just like, la la la, like skipping through a field. Like get some errors, figure out what's wrong. So now we can trace down like, oh, duh, I only fixed one of those indice errors, but I use it twice. So now go back up, the location changed. So let's turn the 2 to a 1 and the 1 to a 0. Now finally, when I run this, I see that there's no errors and it's giving me what I should get. So if I have a line that goes from x equals 0 to x equals 10, and over the course of that goes 0 to 5, has a slope of 1/2. So 2 times 1/2 is 1. Sure enough, it interpolates just the way I want it to. How's that for Python debugging for next time? Maybe I should make the function more complicated, because I think a lot of people were just like, fixed it, done, and move on. It's like, no, you gotta like dig in, like go through the process of like, why is there an error? How do we fix that error? Cool. Yeah.
Can I ask you a question about the next one?
About the next problem or the next
Next topic.
next problem? Yeah.
What is the Euler method? Way of doing calculation?
For Euler method,
Yeah.
this Euler integration.
Yeah.
Oh, awesome. Love Euler method. So this is a differential equation. Have you seen this one before? I mean, k is a constant. I guess you could have some function of time, but we're not going to deal with that. It's a linear, basic, first order differential equation. What is the solution to population? The change in population is k times the current population. What does that mean? What's if I want to know population as a function of time? Yeah, so the solution is P of t is e to the kt. This is an exact analytical solution. So there's no question. I don't need to. There's other stuff that I have to do. I mean, technically, it's not really. Time's a constant, right? And that constant we could say is P at year 0, something like that, or P at year 1900, and we'll say T minus 1900. So this is an exact analytical solution. But with the Euler method, what we'll do instead is, rather than trying to solve for all populations, at every point in time, it's all right, well, if I know the population in the year 1900, then I want to solve for the year 1901. How much did the population grow? That's kind of the basic method for Euler. So in 1900, and I think it's 1.6 billion, something like that. And one way to solve this is solve for the exact solution and then solve for when P is 1901, plug it in. Euler method will do something different. The derivative, the change in the population, is k times that P, the 1900. So it's k times 1.6 E9. So I already know how much it's going to change. So the population in 1901 is going to be population 1900 plus that change in the population times 1 year. So I'm taking one small step into the future and extrapolating, if this change in population was constant for the year, this is where it would end up. And that's a one time step Euler integration. So now instead, let me see if I have. So if I want to go from like 1900 to 2020, and I'll take steps of 1. Or, do you want to do bigger steps? Let's do bigger steps. Steps of like, I think I said 20, so we'll do 20. So I'll say my time step is 20 years, and I want to go from 1900 to 2021. So it's up to, but not including that year, so it should go 2020. The population, I know what the population is in the year 1900, but I don't know 1920, 1940. Yeah.
So if your normal time be like 2020 plus?
We could do that.
So that it actually fluctuates too.
So the way, as long as it's like more than,
It will.
yeah, it'll include that year 2020. So you could do like plus DT. A range gets a little, I don't always use A range when I'm trying to do numerical methods like this. Usually I like lin space, but here we're just talking about like integer steps of years. So A range is good for integer work. It gets a little wacky, like sometimes it'll change length depending on, yeah, how floating point numbers kind of fall into place. But it does, yeah, so the main input for A range and range is like the start, the stop, and then the step size. So but it doesn't include that stop. So if you go more than where you want to go, then you end up in the right spot. And because I want to solve for all these different years, like 1920, 40, 60, 80, all the way up to 2020, I need to create populations at each of those years. So I'm going to create an array full of zeros called initializing my array. Just make it the same length as t. And that first population is this 1.6 10 to the 9. So now I can start at population 1, solve for population 1 as a function of population 0. And once I have that, I can solve for population 2 as a function of 1. So we're taking Euler integral steps through time. And let's write it out to start. So if population 1 is P0 plus K P0 dt, what is population 2, like in the year 1940? What would that one look like? Yeah. Yeah, P1 plus K and then times that P1, right? And hopefully you're kind of seeing like, oh, I should be able to automate this. Like I should be able to create a for loop to do this for me. If not, that's okay. You have a computer, you can copy paste as many times, copy paste replace as many times as you want. Like we could just copy this to 3, replace the ones with 2s, 4, and kind of going down that way. Well, let's see what we got so far for P. Oh, K is not defined. It would help to define it. So far I have my initial condition, then I have in the year 1920, it was around 2 billion, 2 billion, and then 1940, 2.5 billion, and then I haven't calculated the rest. So instead, let's make a for loop that does this thing for us. How does this one look? Will this work for us? You don't think so?
Just the range of 1 is not the index -1.
Okay, yeah. So there's right off the bat, like if we start at 0, P of 0, we already know P of 0, so we don't want to start at 0. We want to start at 1. So we can't, so I could say this is I plus 1, right? Would that fix it? And now this is all I. Would that be better? No? Okay, so now I plus 1, when we go to length of T, now we're asking for, how many do we have? 1, 2, 3, 4, 5, 6, 7. So we're asking for position 7, but we only have, or asking for 8, but we only have 7 values. How did you fix it? So some people are done with this. What did you do? How did you fix it? Oh, I'll show you the error. Yeah, indexing error. Those index errors coming back.
Then we will subtract the length and the T to 1.
Okay, subtract length of T to 1, like subtract by 1. Because the real thing here is like we have 7 values that we're trying to solve for, but one of them we already know. So really we're only calculating 6 different things, or length of T minus 1, right? Like this. But that's Euler method. It's like we're taking this differential equation and using that right-hand side, like the derivative is this, and just calculating what is that derivative. So we don't need that dp dt in our Euler method at all. We're just replacing it with an actual calculation.
But for the analytic one, you also want us to use like the 20-year time steps?
That one, does it matter what the time steps are? Will it change like where the points are? You think so? Yeah, or every year. Because the main thing, like the main difference between using like an analytical solution versus and so Euler method is one of many like numerical integration schemes. But the main thing is that numerical integration, the smaller the time step, the more accurate it is. For analytical, it doesn't matter. You could take 1,000-year time step or a 1-year time step. It doesn't matter how many steps it took to get to time t, it's always going to give you the same answer. So it's nice when you have like an analytical result. The nice part about numerical is that you don't have to do any math. Like I guess technically we're doing math with a computer, but it's always the same math. Like you can always, if you know what the differential equation is, you're not like integrating by parts or anything. It's just, all right, here, plug in these values and step along this way. So it's always the same process, which is nice. But it always helps to compare the answers, right? And then this is a little bit of a personal preference, but also kind of standard, is if you have like discrete points. So when we do Euler method, we don't have a function, we have 7 populations. So what I like to do is indicate that with markers. So markers and lines connect individual discrete points. Versus if I'm trying to plot the analytical solution, that's an actual function. Like all the data in between the points, there are values there. Maybe I didn't calculate them. So when I plot that one, so let's say P analytical is lambda t and we want that So when I compare now without, I would want to put labels in there if I'm trying to actually communicate something, but to start, now I know, okay, this Euler method had solutions at those squares versus that red line. Even if I change the number of steps, all those data points between, they're all there, like I could calculate them. It's a smooth, continuous function. And again, it's kind of standard practice. Partly it's my own preference, but I like to distinguish a numerical discrete computation versus an analytical, like smooth function. And then I feel like there was one more thing to put on. Oh yeah, and then the actual year pop. And let's put that one as like circles. So now I've got actual measured data on there. I have an Euler solution with those blue squares, and then that analytical solution there. What did you say for if time step decreases? If we do 10-year steps instead of 20, or 1-year steps instead of 20, what's going to happen? Yeah. The analytical solution? Why not the orange dots? Why doesn't it get closer to that? Shouldn't it get more accurate? And the orange dots are like, that's our measured stuff, right? Yeah. Okay, actual population is different from a differential equation. Yeah. Yeah, like the fact that we went through the math and said like, oh, this is the perfect solution to this differential equation, it doesn't mean that we found a perfect representation of population. Like we have measured values, and those are not going to change just because we solved a differential equation. So we will, the smaller your time step, the closer you do get to the actual, here I changed it to 1 year steps, and now all those dots are almost on top of that red line. But you won't get to the actual measured values, because those are a little more complicated than just, despite what mathematicians want to make, applied mathematicians want you to believe, like not everything is a perfect differential equation solution. Maybe one day it could be, get everybody stand in line and do what they're supposed to, follow these diffie cues. Are we way over? Oh no, that's the end of time. Yeah, quit harshing my mellow, man. Got stuff to do. All right, thanks a lot. We'll be back on Friday.